In this picture, we can see an example of speed and separation monitoring. There are two laser-guided distance sensors located at the base of the robot stand. As a person moves closer to the robot slows down. The robot's speed will be determined by how far away the person is from the robot's safe zone and by the distance it takes the robot to stop. In this example, once the person gets within 1 meter of the robot, it stops altogether. In this case, the robot itself does not sense the distance to the person and does not sense any collision with a person. The person is excluded from the robot's workspace by the distance sensors at the base of the robot. So it could be argued that this example is not really collaborative, as the person and robot can never move in the same zone at the same time, and the robot should never contact the person. Here are 3 examples with power and force limiting through inherent design or control. Each of these robots has a nominal payload of 500 grams and cannot apply enough force to injure a person with a typical end effector that has rounded edges. It should always be noted, though, that attaching a dangerous end effector, for example, a needle, will mean the work cell will need additional safety screening to prevent possible injury to a person. These robots can easily be hand-guided to teach positions without fear of operator injury. They can be intermixed with people on the same manufacturing line, allowing people to do more complex operations and the robot to perform simple operations. These robots can typically move at speeds up to 1.5 meters per second and bump into an operator without injuring the person. In this video, we see a low-power collaborative robot that is inherently safe by design. An operator can even put his hand into the pinch point of this robot, and the robot will stop automatically without injuring the operator. This is a much faster response than trying to find and press an e-stop button. In addition, there is work going on now that explores the use of capacitive sensors to detect people from a distance and slow down or stop a robot. Most of these sensors work up to a maximum distance of about 200 millimeters. They are likely to be most useful for relatively low payload robots moving at moderate speeds of less than 1 meter per second. They require antennas hidden under the robot cover, which can sense distance in the direction of motion. This class of technology is being developed for hand gesture sensing in automotive applications, and as a result, may become cost-effective and reliable in a few years. ISO 10218-2 and ISO TS 15066 both address the design of safe work cells where the robot has additional application tooling installed. Even a safe robot can be dangerous with a dangerous end effector or loading a dangerous process, for example, a stamping machine. What may be less obvious is potential danger from the motion path and speeds of the robot through the work cell. As will be described later in the session on testing, it takes much less force to stop a collaborative robot in free space, where there is room for an operator to slow down the robot over some distance, than to stop a robot when it traps an operator against a rigid surface. Consequently, work cells should be designed and the robot motion path within the work cells programmed, with the robot speed adjusted for the distance to the nearest rigid surface. The farther away the robot is from a rigid surface, the faster it can go, up to free space speeds of 1 to 2 meters per second. However, as the robot approaches a rigid surface, it should be programmed to slow down so that if it traps an operator against the rigid surface, the forces will not exceed the allowable standards. In the example in the graphic, the 100% joint speeds of the robot are set to values that allow higher speed motions, for example, 1 meter per second, while the 100% Cartesian speeds are set to much lower values, for example, 1/10 of a meter per second. When the robot is inserting parts into fixtures, the Cartesian mode is used, and this greatly reduces the speeds for the last 100 millimeters of motion down into the fixture. In this example, the fixture approach distances are set to 100 millimeters above the fixture so that the higher speed joint motions cannot track the operator against the fixture. It is also important that any controls necessary to operate or stop the robot in a safe manner be obvious and simple to use, or built into the collaborative operation of the robot. Historically, workcell designers would place one or more large red e-stop buttons in robot workcells. However, when operators are inside the workcell, and perhaps even guiding the robot around by hand, workcell e-stop buttons may not be easily accessible to the operator. So the operator should be able to stop the robot by just pushing on it. It is also important to consider any cases where the robot may move while the operator is inside the collaborative workspace and may be startled by the robot. It is a good idea to avoid sharp edges in all parts of the workspace and to protect an operator who may be startled.